Hi everybody, I'm Chris Kanish and this is Tricks of the Trade, learning how to learn computer science. Today's lecture is on using the terminal. Let's get started. So when we think about using a terminal or using a shell or using a command line, these are all usually kind of interchangeable. Fundamentally, what we're talking about is how we use that main program that allows us to use the computer. There are lots of different ways we can do this, right? In Windows, we can come down to the Start menu and we can click on a program and that will launch that program and we can do whatever we want to do with that program. And then once we're done with it, we can go back to that shell, back to the Start menu in this instance, and launch another program. Maybe we can even launch 2 programs at a time, switch between them, all that type of thing. On a phone we could use a launcher or a home screen, these types of things to just go through all the different programs, run them, switch between them, maybe switch from one program to another. Like if you click on a mail to link in one program, you want to go over to your mail program, or when you click on a URL, that type of thing. That's fundamentally what a shell is going to do for you. So what we have right here in front of us in this Visual Studio Code window is a shell. This is the same thing functionally as a Start menu or a home screen, but it's a lot more terrifying because it's not nearly as easy to use, right? We're not just flicking through lots of different icons and tapping on them. We don't have any idea of how to use this by default. But even though it has this really steep learning curve, even though it's not super user-friendly to begin with, it's an incredibly powerful way to use your computer. And shells like this were designed back in the day when so many of the people who used computers also programmed computers at the same time. So shells actually have this really cool property where they're both a way to just launch other programs, as well as a way to write programs which will then coordinate all of the other programs that are running on your computer. This is an incredibly powerful way to use computers. And in CS361, we're going to learn how to write a shell like this. But in order to know what's so special about writing a shell and actually the innards of it, we want to just know how to use one to begin with. So that's what we're going to go over the course of this video. So the first thing that we want to talk about is the most basic thing we want to do with this shell. Just like with the Start menu, we want to say, for instance, launch some programs. So a program that I could launch would be the ls program. So I can type ls, hit enter. That gives me a list of files that are in the directory that I am in. ls is a program, it runs, it does what it needs to do, and then it transfers control back to that terminal. A little bit about the Unix philosophy, a little bit about the basics of programs and files, because fundamentally on a Linux machine, everything that you're going to touch, everything that's ever relevant for you is a file. So ls here is a file. I can find out where that file is by doing which ls. This tells me what my shell thinks is the location of the program ls that I want to run in this scenario. So at this point, we want to talk about paths and file systems and files and relative paths and all of these things. This is a really important prerequisite for learning about how shells operate and get the job done that they want to get done. Every time you are using a shell, you are in a specific directory. Sometimes it's called your current working directory. Sometimes it's called your present working directory. You can find what that is by typing pwd and hitting enter. That tells you what directory you are in of that file system. And when I do ls, I just see the files that are in that directory. Now, if I want to refer to one of those files, say I want to concatenate the content of that file to the screen, I would just run the cat program and then type the name of one of those files. So that is a file that is in that directory. And the cat program is instantiated. I can find where that cat program is by saying which cat, and it shows me, oh, that's where that file is. That is a Unix executable. If I want to see what type of file it is, I can run file bin cat, and that tells me what type of file it is. So this is saying to me that it is a Linux executable, and it has a whole bunch of other useful details about that Linux executable. But at the end of the day, what we care about here is that this is a program that can be run by your Linux operating system. How did my shell know when I typed pwd, I wanted /bin/pwd? Answer to that question is the path environment variable. So we got 2 really important concepts bundled in here. One is that there's a set of variables called environment variables that are just instantiated when you start a shell. There's a lot of variables that your shell is going to use to just get its job done. For instance, so if I want to show what those variable values are, I can echo them onto the screen. So what echo will do is it will just show me the text that it sees, but it can also interpret specific variable names, and variables in the bash shell at least use a $ and then the name of the variable. So if I want to echo my home directory, I can see that the home directory is /home/cknish. If I want to see what my username is, I can do $user. Now, if I want to see what list of directories I can potentially pull programs from, that one is path. This is a very important directory. This is a very important variable. And as you can see, there's lots of places that I could potentially pull an executable from, mainly because I'm using Windows Subsystem for Linux, and it has this special property where it can run both Unix programs from the fake little Unix that's running inside of my Windows machine, as well as Windows programs just through the normal way that Windows runs programs. So if I were to run calc.exe, it will open the calculator. Let's see. Yeah, so it opened that calculator behind my Visual Studio Code window. That's a pretty cool part of using WSL. So we have these variables. We can also define our own variables. And this gets into that concept of shells are both a way to run programs as well as a way to write mini programs that you can use to control the operation of other larger programs. So if I wanted to create a variable called awesome equals heck yeah, I could create it like that. I just take the name of the variable equals what I want to set it as, and I'm done. So if I want to say echo am I awesome? Awesome. And that's what you get. That is just a variable substitution coming out of running that echo command. Now, I started talking a little bit about paths and programs. Let's go back to that topic. When we talk about a file in Linux or in any Unix derivative, that file is always going to live somewhere within the file system. If we really needed to, every time we ever talk about a file, we could talk about its absolute path, a path that starts with a slash that represents the root of that file system. So at this point in time, in this shell, my shell is currently operating in the root directory. So there's /bin, /etc, /home, lots of different very standardized directories that exist within the root of a Unix-based operating system. And every single file will have a name that represents some location within this hierarchy of either directories or files. Right? We have a directory, and this will work just like it does in Windows, where a directory has things inside of it, which could also be directories, which will have things inside of it, which can then either be directories or files. You can have those anywhere. So I could potentially have a file here at the root. Let's see if I can touch this up. I don't have permission to create a new file here, so maybe I'm going to yell at it and let me do that. So yeah, now I have a file called ASDF. I can tell that it's a file A because my syntax highlighting of ls here is showing me that it's white, so that means it's a normal file, whereas blue is a directory, and green, I believe, is an executable file, things along those lines. So let's find out file init. So yeah, init is a program. ASDF is an empty file, and all these other things are directories. So bin there, see, is a directory. So one really quick thing here. So when I do sudo something, that allows me to elevate a shell, just as a really quick thing. But if I'm doing something that doesn't have permission, but it's my computer, I know whether I should be doing something or not, I can use sudo and then that program. One other really useful way to do this is, let's do rm asdf. It's going to say, no, you can't do that, even if you try to, right? If I want to run that same exact command using the bash shell, again, I can just do sudo bang bang. So bang is programmer speak for exclamation point, and that will rerun the previous command, but with sudo pre-pended to it. So you can see it give me a nice little hint here of I was running sudo rm that ASDF file, and now that ASDF file is gone. pretty spectacular, right? I keep getting distracted. We're talking about paths. And the really important concept I want to cover here that trips a lot of people up is super basic, or I keep getting distracted. What I'm trying to talk about right now is paths. We've been talking about paths, we talk about the root. So we're talking about paths. We're talking about the root of the file system, and every single file in a Unix-derived operating system will exist somewhere in relation to that root. Now remember, when you think about a Windows machine, you don't have a one single root. You usually have different devices like your C drive and your D drive and things like that. And that's where files come from. What Unix said was everything is a file and everything exists within one file system. And it has a location within that hierarchy of directories and then subdirectories and files and directories within directories, stuff like that. The really powerful thing that we're going to be able to do then is refer to files in one of a few different ways. So let's go back to our home directory. Here we've got a few different files. There's 3 ways we're going to refer to files in any Unix system. One is just implicitly we can refer to a file in the current working directory via its name. So if I want to cat filename.txt, I can just cat and then filename.txt. What most programs will do when they're looking for files, if they're given the name of a file that doesn't start with a slash, they will immediately say, aha, this is a file which is in my current working directory. Just assume it's there, look for it there, test to see if it's there. If it's there, print it out to the screen if that's what the cat program is going to do. Then there's 2 other more explicit ways to refer to a file. One is with a relative path, where we talk about where the file is explicitly with respect to what directory we're currently in. So if I go into this repos directory and I want to talk about the file name, I can talk about it in relation to where I am. File name is in the parent directory, so I can cat period. So I can cat period filename.txt, and that will look for it in the parent directory to where I am, and that's that file. That will show me where it is there. If I have some files in here, let's go back down. And if I want to talk about something relative to here, again, I can talk about it as ls I can do period/repos and website. So that is a directory that exists relative to where I am. My shell has a current working directory of my home directory, and repos/website is relative to where I am right now. I can also talk about it as an absolute path. So the way we define an absolute path is something that starts with a slash. The way we define a relative path is anything else that does not start with an absolute or with a /. Everything else is with respect to what directory you are in at that point in time. There's a few relatively complicated rules for exactly how you compute that, but we're going to go over these concepts right now. So absolute paths. If I want to talk about the repos/website from where I am right now, I know that I'm in this directory. And so if I want to say ls home/repos website, oh, I did not spell it correctly. So I just did 2 things right there that are super useful ways to make things faster. One is I was doing movement within the line by using some keybinds, and I was using a concept called tab complete. So with the movement, so I'm hitting up to go back in my history of what commands I've been doing in the shell. Also crazy useful. So here, if I want to move backwards and forwards, by default, if those keys aren't binded by something else, I know when I use terminal on macOS, I have to delete some key binds or change some things to allow this to work. But Bash will take Alt-B and Alt-F as go back 1 word, go forward 1 word. So it looks for anything that's not alphanumeric, and it hops back and forth that way. So I can go back, I can go forward. So when I have this line and I knew I had to change that ckimage part, I can go back, and hit forward. I can also erase an entire word by doing Alt plus backspace and then retype it. That works out super well. Another thing here I'm using is I'm Control-C'ing to kill a line without actually running it and start over. So if you're typing something and you're like, oh, that's not the right command, I don't even need to do that. You don't need to sit here, wait, for the entire line to get deleted. You can have your whole big line and be like, screw this, and then you can hit Control-C and you move on to the next line. These are all just a million different things that make you just a little bit faster at doing computer science stuff, but this helps you get past the brain dead stuff so you can get to the hard stuff and keep your brain running at the level it needs to run to do the hard stuff. I'm rocking my entire table here. I'm just so psyched. A few other editing shortcuts. A lot of these things are personal preference of like, find the way to use the shell as easily and quickly and efficiently as you can. If these aren't the types of shortcuts that make you faster, I don't care, right? I want you to find things that make doing the dumb stuff easy and fast so that you have more time for the hard stuff so that you can get better at the hard stuff. Another really powerful thing that most modern shells can do is they understand the context of the file system, and a lot of the times they know what you're trying to do at any given point in time. So if I am trying to say cat from file to the screen, and I start trying to cat filename.txt, if I type file and then I hit tab, it will automatically fill in that entire file name for me, which is super, super useful. How did it do that? The shell knew what directory I was in, and it knew that if I started typing something and then I hit tab, what I meant was, I know it's a file and it starts with this, but I don't want to type the whole thing because I'm a lazy human and I know that you're a computer that'll do my bidding. I'm just going to hit tab and make you list all the files in the directory and pick one based on the prefix that I had already typed in. There's nothing else in this directory called fil blah, 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 blah. So let's say I said touch file stuff.txt. So now there's two things that start with fil. So if I do fil tab, nothing happens because there's no one thing that will just finish this out. But if I hit tab twice, it's going to show me, oh, I'm sorry. Let's do cat fil. If I hit tab once here, it will expand out to E because it knows every single thing that could start with fil in this directory is either fil, like file name, or file stuff. But then it stops there, and because it's ambiguous. So if I hit tab twice here, it's going to say, okay, well, you either meant file stuff or file name. It'll just give me a little reminder, what is it that you meant? So I can just hit a capital S here if I meant stuff, hit tab, and it types it all out for me. While this is useful in that it saves you like 200 milliseconds to not type out the rest of that word, what's also arguably like more useful and important about this is that it cuts down on human error. Right? When we saw earlier on, I was typing everything manually myself as part of this demo. When I wanted to say cat home cknish and I typed kc instead, what I would typically do if I was just going fast and normal, I would hit tab here. And as soon as I hit tab here and I didn't see it expand out, I'd be like, oh, I probably typed something wrong. So I can see it, see that error, type it in, and I can keep going like that. That's usually the way that I will navigate to a specific directory. That makes things just a tiny bit faster, but it also helps cut down on human error typos, which is really, really helpful when you're working at the command line because it's not super forgiving. You type one thing incorrectly and the entire command doesn't work properly. Super bummer. So that's a lot of the just basic useful stuff. This is a good kind of foundation on which to build a efficient use of the shell. A few other useful things that we want to know about now that are really, really useful, but later on they're going to be much more useful, especially in CS361, is input and output redirection. So when we use a program in a Unix-based operating system, very often a lot of these utilities are going to be based on this idea where we take every program and it takes its input on a thing called standard in, which is a file descriptor. So it's going to receive a stream of characters as input. It's going to read those in, and then it's going to process them in some way. And then it is going to send its output along a stream of characters called standard out. And if we write all of our utilities that do useful things in this way, where we like bring a specific set of things in, we process them and we send a specific set of things out, just one input, one output, we can connect those things all together in a really useful way to do actually kind of complicated stuff. So I'm going to show you a little demo of how that works and why that might be useful right now. So if I want to do use this concept of input and output. Let's see. So if I do cat a file, if I do cat file name.txt, this will by default send the output to the screen. Like by default, every program is going to send its output to the screen. What I want to do in some situations is take that output and store it into a file. So I'm going to redirect that output to a file. Let's do file name extras.txt. Oh, no, sorry. And I put a caret or a greater than symbol there, so that will do output redirection. So take what comes out of here. It was the alligator from like greater than less than. So the alligator is going to drink in all of the things that you had come out of your program, and it's going to save them into that file. Likewise, and so now if I do a cat of extras, oh, no, I didn't actually run it. I Control-C'd it. So cat file name into extras.txt, and now if I cat extras to the screen, it's the same thing as file name. I can do diff file name extras, and it's going to show me nothing. So the diff program will show me what's different between two files, and if there's no output, that means that there's no difference between them. Now, the next thing that I would like to do is input redirection. So if I want to, say, count the number of lines in a file, I can use the wc program. So I can do wc file name.txt. This counts the number of lines, words, and characters in a file. So there's 2 lines, 12 words, and 56 characters in file name.txt. You can count those up, make sure that that's true. What else we can do is, instead of using wc that way, we can use it in that standard input, output, do one thing, do it well mode that I mentioned before, and have it read its input from its, not from a file name on the command line, but from its standard input. So I can do wc and I can input redirect from file name.txt, and it will give me the same thing. But here, it doesn't know what file name it is because it doesn't really care. It's saying my job as a wc executable is to do one thing. It's to take in a bunch of stuff on my input, count the lines, count the words, count the characters, and send them out standard output. And that's what it does. So there's just a few other relatively advanced shell things that we can do. We can do input and output redirection, where we take a specific file, so cat file name.txt, and we can redirect its output rather than sending it to the screen. We can send it to newfile.txt, and now newfile.txt has the same content as filename.txt. We can also use input redirection, where we send the input to a program rather than reading it from the screen. So cat will read from the screen, and then it will print to a file. So if I have a file called zxcv, and I just say this is going into that file, and then I hit Control-D, which sends the end of file character, kind of special and important there. What will happen now is zxcv will have that contents in it. Pretty cool. What that did was it read from standard in, which is just me typing at the computer until the end of file character shows up, and it read that in from standard in, and it shoved it out to its standard out, which was connected to this file zxcv.txt. What I could do instead is cat from a file zxcv into a file astf, and that is both input and output redirection through that program cat. So cat, like so many other Unix utilities, does one thing, which is concatenate files to standard out, and it can read those things it needs to concatenate from standard in just as easily as from the file system. Why do we call it concatenate? What does that even mean? So what we could do here is, sometimes the most logical way to think about what cat means is, if I want to concatenate multiple files, I can do it like this, right? So that's actually concatenating in the English meaning of the word, where I take all of these different files and I slam them all together out onto one standard out there. So I can do that, and I can send that out to 2lines.txt, and 2lines.txt has both of those lines in it. I want to take the output of one program and use it as the input to another program, which gives us the fundamental Unix pipeline utility-based model. I can say nl So if I want to like count the number of words in 2lines.txt, I can also find I can number 2lines.txt, and so that gives me like one extra word per line. I can take the output of this program and I can pipe it into WC, and that will count up all of the total lines, words, and characters in this file. So this added 1, 2, 3, 4, 5, 6 characters. And then this right here is a tab character. Super tricky, but I know. So there's 1, 2, 3, 4, 5, 6, 7 characters. So we go from 58 to 72, and that makes sense. How did I know that was a tab character? Well, I edited out a whole bunch of me troubleshooting that. And the way that I can troubleshoot this is by running Hexdump. This will take, instead of showing me this file on the command line, I can actually look at it in a easy to digest human form as opposed to like, or hacker form, I guess you could say, instead of a human form of this file. So NL 2 lines, and then I'm going to pipe that to hexdump.c or -c. So what this gives me on the left is the hexadecimal representation of every single byte that's stored in that file. And on the right side, I get like a nice, easy, human readable version. So 20 here, hex 20 stands for the space character. Hex 31 is the ASCII 1. Hex 09, if we were to pull up a C table right now, you would see that hex 9 stands for the tab character. And then these are just the characters of the word this, it, space, is, space, etc., etc. So that's another useful program and another great example of how to pipe things from one place to another, right? I wanted to see what the output of this program looked like byte by byte. And so I took the output of that program and I piped it to a program that I know will take its input and show me exactly what the bytes are that were sent as input to that program. And the -c allows us to see the human readable alongside the machine readable version. So if I were to do this without it, it just shows me hex, which, you know, I'm not the super hacker that I wish I was, so I could say, oh yeah, I know exactly what's happening there. I would have no idea. A few other more advanced things that you can do here with the shell, like write for loops, do subshells, things along those lines, but I'm gonna leave that for talking about during class, or if other people have questions, or if you wanna find demos on YouTube, I'm sure you can find some really good ones. Feel free to post good stuff that you find in the comments on Piazza. Thanks a lot for watching, and I'll see you next time.